Hi and welcome back. In this segment, we're going to look at using online resources to obtain and evaluate solar energy information. By the end of this section, you should be able to use an insolation map to define approximate insolation values. You should be able to use online data resources to get localized insolation values, and then evaluate the different ways insolation can be reported. Let's first begin with the definition of solar insolation. Well, we previously reviewed this map of sunlight energy from the National Renewable Energy Lab. Maps like this provide information for both fixed systems as well as tracking systems. But how do we begin to think about how tilt or direction might impact insolation? Insolation is an acronym consisting of three abbreviated words: incident solar radiation. And it essentially means the quantity of sunlight energy that reaches a surface. As a review, the sun goes from east to west daily. In the northern hemisphere, the sun is in the southern part of the sky. In the winter, the sun is lower in the sky, and in the summer, the sun is higher in the sky. In the southern hemisphere, everything is opposite, with the sun being in the northern part of the sky. In order to put some numerical values to the insolation maps, we can use a small handheld power meter. But this doesn't give us annual data or data over many decades that we've collected it. There are databases available to us that provide these data. The visual NSRDB, the National Solar Radiation Database, as well as an older textual version of that database, give us some additional pieces of information that we'll talk about shortly. There's also a tool called PV Watts, which is used readily by designers, integrators, and installers, and we'll discuss that in later modules. Let's first start with this NSRDB, the National Solar Radiation Database. This was developed by the National Renewable Energy Lab, and there's a solar radiation map for the entire United States, parts of South America, and India. The NSRDB has a lot of information that you can download, and it extends beyond just photovoltaics, such as land ownership, power plants, and other political borders. All the information is downloadable as a spreadsheet format or can be integrated into GIS platforms. At this stage, we pretty much just want to look at the insolation maps though. So when we go into the NSRDB, one of the pieces that we could look at would be the global horizontal insolation, which is the combination of the direct sunlight and the diffuse sunlight added together, and that's how this color map is constructed. By clicking on any location that has a color map, you'll get a data table that shows the GHI, Global Horizontal Insolation, value for that location. In this case, the global horizontal insolation is 5 kilowatt hours per square meter per day, or 5 full sun hours. This is for collectors placed at latitude tilt, meaning if you live at a location with a 41-degree latitude, the GHI is given for a collector tilted at 41 degrees. It does not take into account the different roof pitches that one might have on their building or changes in azimuth orientation deviating from due south. To look at that a little more closely, we need a slightly different data set. Some of the older data sets are more useful for analyzing variations like the tilt and orientation. An older version of the National Solar Radiation Database is still accessible, and it shows data for almost 3 decades. It contains monthly insolation values with variations in tilt. Because it does this over a 30-year average, we don't have to be concerned with 1 day or 1 month of non-typical weather. Let's look at the information contained in the Solar Radiation Database spreadsheet. In this example, I've downloaded and imported insolation data for Colorado Springs, Colorado. The data give us the latitude of that location, 38.82 degrees, and then it gives us another piece of information. It's provided for flat plate collectors facing south at a fixed tilt. What that means is that this is not a tracking system and the panel is faced directly due south. It then gives us daily insolation based upon tilt angle for each month, as well as the average over the year. There are always 5 values that are listed here: a tilt of 0 degrees, which would be flat, latitude angle minus 15 degrees, latitude angle, and latitude plus 15 degrees, and 90 degrees. 90 degrees would be what we'd consider vertical. Latitude represents insolation when the collector is at the same angle as the geographic location, which is 38.82 degrees. Latitude minus 15 would be 38.82 minus 15 degrees, which would be a collector at about 23.82 degrees. and latitude plus 15 would be 38.82 plus 15, or 53.82 degrees to horizontal. We're only concerned with the average values shown in this table: 4.7, 5.5, 5.6, 5.4, and 3.8, which are the average insolation values per day for a typical year at those angles. We receive the most insolation at latitude tilt in this case, 5.6 full sun hours per day. At latitude minus 15, however, we would get slightly less energy, only 5.5 full sun hours per day. In the next section, we'll use this information to position solar panels for optimal energy production.